Great. And I think the meeting is live streaming now. Let me just check. Oh no, why is it doing this? It's saying it's not gonna live stream for another 5 minutes. That's great. Okay. Good. Perfect. Let me just make a note of the live stream link and we're ready to go. Okay. So I think we were here yesterday. Okay, so we came up with let me just clean this up. This watermelon solution. Basically, our solution was just like, hey, if W% 2 and W is not equal to 2, right? So if it's greater than 2, then print. Yes, you can split it up evenly, otherwise print no, or not evenly, but at least there's some way of splitting it up that everyone gets a even number of kilos. Otherwise you print no. Okay. So hopefully 1 and 2 made sense to people. Three, okay, is the elections in which 3 candidates participated have recently ended. The first candidate received A votes, the second one received B votes, the third one received C votes. For each candidate, solve the following problem. How many votes should be added to this candidate so that he wins the election? I.e., the number of votes for this candidate was strictly greater than the number of votes for any other candidate. Please note that for each candidate, it's necessary to solve this problem independently, right? So we're not adding, we're not using the votes that we added for candidate A to win, to calculate how many does candidate B need to win and things like that, right? Okay, so does anyone want to help me out with this problem? Any thoughts on how to start on your? Can you help us with this, please? Okay, Jacob has put something in the chat. Minu. Oh, Minu's here.
I'm just putting up what I wrote.
Mhm. Okay, I like some of these. Okay, so I'm just gonna start off by initializing these to like certain values just to make our I don't want to like have to type in the same values every single time. So let's just hard code some starting values for now. And then so Jacob has if people look at the chat, he's created this function called vote adding, and basically he's checking for A and saying, hey, if it's already greater than B and C, A already won. Otherwise, let's find the difference for B and C and see, okay, how many votes are needed for B and C to win? And it's basically whatever is the difference for A and B. Um, Oh, sorry. This is I see. So you're checking how many notes are needed for B to win and how many notes are needed for C to win. So basically A minus B, that's the number of votes that B would need to tie A, and then plus 1 in order to win. And same thing for C, right? And then he does the other kind of combinations of or permutations of this. So if B is greater than A and C, then B is already won. And so, 0 votes are needed. And then for A and C, basically you need the difference between B and A plus 1 or B and C plus 1, right? And yeah, same thing for C. Great. Minu did, she has a add votes function where we can put in A, B, and C. And basically it's telling us, okay, so this is telling us for candidate A, how many more votes does candidate A need to win? And so if A is greater than B and A is greater than C, we've already won. If B is greater than C, then we just have to basically beat B, and then if C is the greatest, then we have to beat C. And so this works for finding it for one candidate, and then for the other two candidate, like to find it for all three candidates, you could always just call it for a different function, or sorry, call the function on a different order of candidates, if that makes sense. So let me type this up. And what Minu is doing is not necessarily different from what Jacob did, right? But she uses a function that allows us to kind of use this comparison thing multiple times without having to rewrite the same thing over and over again. So if you remember yesterday, that principle I mentioned of what's called dry, don't repeat yourself, right? We don't want to repeat ourselves more than necessary. So if there's a way to take that duplicate logic and just put it into a function, we want to use that, right? So that's, I think, what Minu has done. Oops. And this is, I should say Ella, B is greater than or equal to C, else this. What I've done is technically equivalent to what Minu has done, but what she all did is she was like, hey, I mean, it doesn't really matter if we make this an elif case or if case, right? Even if this is a separate if statement, this if statement has already returned. So we only reach here if this is not true. That makes sense. So I can do this, and then I don't also need this else case. I can just keep it as like a separate case. And sometimes when you're coding, right, you'll have what's called a linter, which is something that will kind of check your code, format your code, maybe try to help you avoid common errors and say like, hey, you're using code in this way. Are you really sure you meant to do that? Like you have this variable, you've never defined it before, but you have a very similar named variable above here. Maybe you made a typo, things like that is what a linter does. And so a linter might have thrown an error for what I had before here because it will say, hey, you don't have a case like you don't have a return statement in all cases. If I were to, well, let's pretend. Uh, let me think. Yeah. So yeah, a linter may not be smart enough to realize that like that we're always going to execute at least this else case, if not these first two cases. So by making it more explicit by just having this case outside of the if statement, it might be a little safer and easier to also maybe process the code. So this is good what Minu has done, but now we need to just basically call add votes on candidate A, B, C, and then BCA, and then CBA or CAB. It doesn't really matter what the order is of the last two. We just need to make sure that each of the candidates has a turn in that first position. Now, what Evan has done is just like, I'm doing a one-liner. Let's go. Let's make this elegant. Let's create a function called add votes A, B, C. And he's realizing like, hey, I don't even need an if technically statement because max is a thing inside of Python. I can compare multiple elements at once. I mean, internally, max is still comparing two at a time, but we can put in multiple elements here. And so he says, okay, if C minus A is something that we're, positive, right? Then this plus one, right? If C had the most votes, then this would be the greatest number. If B had the most votes, this second one would be the greatest number. And if both C and B were smaller than A, this zero would be the greatest number. And so no matter who's the greatest, right? Whatever is the maximum of these three will give us how many votes is needed for A to win, right? And then once again, we just have to call this add votes function on all three candidates, giving each candidate a chance to be in the first position. So this works really well. And Manish is just like, hey man, I don't want to keep calculating the most votes. Let me just calculate one time. This is something I really like. So he said, hey, let's do max A, B, C. Right, this avoids kind of unnecessary computation. And then whatever this max votes is, we can just do A minus max votes plus 1. If they're not equivalent, right? If oh, actually, let me think about this. Let's think about this. Def votes needed, votes received. Votes needed is not equal to most votes. Blah, 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 blah. Ooh, okay. This is interesting. So this is it's tricky. It might be subtle, but let's see if we can see if there's any edge cases that we might reach with this. So you don't have to, by the way, specify return none, right? If the default thing that the default behavior is to return none, I mean, it could be good coding style to explicitly say that, but in this case, if we don't expect any return values, it's fine. If we're not doing anything with the return from this function. So, if there were like, some cases where we're returning an actual value and then in some other cases we're returning none, it's good to put that explicitly. But otherwise, if in all cases we're returning none, you don't need to necessarily put it. But okay, so does the what Manish have here work? Can someone say, oh, I should probably name the variables the same thing he did. Okay. Does this work? This code by Manish? What do people think? Oh, let me see. Okay. So let's talk about edge cases. Okay, so what do we know about votes? Votes always have to be some integer, right? And it's not negative, right? You can't receive -2 votes. You can receive 2.5 votes. You receive 0 votes, 1 vote, 2 votes, at least 0 votes. Okay. So edge cases. What are edge cases? For example, one edge case that's always good to have is, sometimes it's like, does this actually work for maybe values of 0 or 1, right? Does this work for if you have multiple numbers? Does it work for when like all 3 numbers are the same or for when 2 of the numbers are the same? So let's try that actually. Let's say A equals 0. I mean, this is the, a great edge case because it fulfills a lot of criteria, right? Now, not only are we testing this, does this work for 0? We're testing, does this still work when all 3 are the same, right? Because there's some comparison going on, so we need to make sure that, we don't just test this for a simple case when things are different, but also when things are the same. So if I run this, how many votes are needed for A, B, and C to win? According to this, it's 0. Manish, do you think you know what's going on here? And like, is this correct, first of all?
Uh, Wait, so what values did you use in this one?
Here I use A equals 0, B equals 0, and C equals 0. Oops, sorry.
Oh, no, it doesn't. Wait, but shouldn't the max still be, if the max is 0 and votes received is 0, shouldn't it be 0 plus 1 minus 1? Or is that not how the max function works?
So are you talking about here? Like, so
Yeah.
this is returning 0. Yes, that's right. Let's just print out most votes. So this returns 0, that's right. But here's the thing. Do we go into this part of this if statement? If votes received is not equal to most votes, that's only when we go into here, right?
Oh, right. Yeah, okay.
And so otherwise we print 0. So the assumption here is we assume, and like in a large election, that's probably going to be the case. It's very unlikely for two candidates to have the exact same number of votes. But if two candidates do have the exact same number of votes, one of those candidates does need to win outright in order to actually win, which means that each candidate in this case would need one vote to win since they're all tied right now. So this is perhaps how I would have also done it, because I was like, hey, why should I be recomputing the max each time? But we lose a bit of information here, which is we don't realize, does any other candidate have the exact same number of votes as us? We only know if we tied with most votes, but we don't know if we are the only candidate with most votes. So here, since we're comparing multiple times, like in Jacob and Mina's solution or Evan's solution, we do more comparisons, right? So it feels a little wasteful, but it is kind of necessary because we need to know, like, hey, do multiple candidates have this? Okay, but one thing we could do to maybe modify Manisha's solution a bit is basically, instead of using the max function, we'll manually calculate it using an if statement. It's going to take the same amount of time as max would, because that's exactly what max is doing under the hood, right? But then in that if else statement, we also maybe count something like 2 people actually have the same number of votes, or 3 people have the same number of votes, right? So then we can basically check, hey, do we have to has anyone else tied with us, right? And then once we know someone else is tied with us, we can just add 1. So yeah, I think it's obviously not too far off from working, but this is a really good example of like how an elegant solution sometimes unfortunately needs a little bit of modification just to make edge cases work. But okay, hopefully that was like simple enough and people understood that problem, because 4 I know was a doozy. Okay, so some number of people, which is it's an even number, right? They've stood in a circle, and the people stand in the circle evenly. They're numbered clockwise, starting from a person with the number 1. Each person is looking through the circle center at the opposite person. So in this case, we have a sample of 6 people, right? Is there any pattern that you notice between like the numbers of the people who are looking opposite each other? Can someone help us?
It's a difference of 3 each time,
It's a difference of 3 each time. Nice.
and
Nice.
that's half the total number of spots.
Yes. So that 3 is not just a random number. It's exactly half of 6. Good. So you don't know the exact number of people standing in the circle, but this number is even, no doubt. It is known that the person with the number A is looking at the person with the number B, and vice versa, of course. What is the number associated with a person being looked at by the person with the number C? If for the specified A, B, and C, no such circle exists, output -1. So in this case, we have case 1, we have 6, 2, and 4. So we're given one piece of information, which is what is A and B. And these are the 2 people who are looking opposite each other. So what can we do with the 6 and 2? Well, we can figure out what is the size of the overall circle, or if there is even a circle that can fit such a combination of people. So A and B, that is determining the size of the circle. And then once we have the size of the circle determined, we can hopefully figure out, hey, who does C look at? Who does person C look at? Okay. So do people understand these 3 test cases and like why some of them return positive numbers and some return -1? So in this case, 6 and 2, it's possible to figure out, okay, there's a circle of 8 that this works for. And then in this case, 4 would be opposite person 8. In case 2, for 2 and 3 to be standing next to each other, right? Like for people with just a difference of 1, being able to look directly at each other, that means that the circle has to consist of 2 people. But if the circle consists of 2 people, then there's no third person, which makes this make no sense. So this does not occur. It's -1, right? For case number 3, 2, and 4, so for a circle of 4 people, this works, right? That the difference of 2 people looking at each other is 2. However, if we just have a circle of 4 people, then there is no person 10, And so again, this returns -1 for does not occur. Okay, so how do we solve this? We have we have a lot of solutions in the chat. But Anirudh, did this make sense? I know you were saying you didn't quite understand the problem. Okay. Why don't you help me write some code to figure out how to, first of all, determine the size of the circle just from using A and B. Let's say we have a function that says, find opposite C. Let's call it that, A, B, C. First, what we want to do is find circle size. And for that, we need A and B, right? Can you help me implement this find circle size function, please?
Return
Or
2 times the absolute value of A and B minus B. What?
so sorry, just I want Anirudh to get this one just because he said he had some problems on the homework. So yes, but yes, I mean that I do see you in the chat. I do say that's correct. But yeah, Anirudh, how would you do this?
Probably you can subtract something with like, because in case 1 is like 6 minus 2 is 4, and then 2 times 4 is 8. So
we could do A minus B times 2. Sure.
yeah,
Does this always work?
I'm not too sure. Probably
So this works if A is greater than B, perhaps. But as Evan pointed out, it might not always be, right? B could be greater, right? So then we have to take the absolute value, right? So now we get what Evan had given us, which is this. But does this actually solve it for all cases? So I think we need to make sure that we're accounting for something like case 2. And by the way, I gave you some more example cases here. I mean, all of these problems I think had example cases. For some of them, I omitted them. But for this one, I wanted to just kind of be nice and help you guys think of the edge cases. So I don't know if all the solutions in the chat consider this edge case, but let's see. So what edge case do we need to consider? Let's say we have circle size equals blah. Okay. How do we account for case 2 here? Like, let's return -1 from this function if this is an impossible circle to have formed, right? So how do we account for case 2 in this function? Okay, this is open to anyone.
You can account for case 2 by saying that if circle size is less than either A, B, or C, then return -1.
Yeah, sure. Why not put it C in here as well? Let's just do that. Yeah. And I guess this also then accounts for case 3. Right. Okay. So basically, if circle size equals -1, then return -1. Otherwise, we have a valid circle and we have a valid circle size. No more edge cases where, we should be returning -1. How do we figure out who's standing opposite C? I think, okay, I see this something like this in Evan's solution, Jacob's solution, Manish's solution, and Mina's solution. Okay, so everyone here should be able to tell me something that we could use. Anyone feel particularly confident in their solution and want me to?
You could test mine.
Okay, let's go through Jacob's. So check if circle size is even. Okay. So D is equal to temp over 2 plus C. So that would be in our case circle size, I think, over 2. plus C. But then you also have this D finder.
Yeah, that's my function.
Let's see. It's at the top. Yes, thank you. I see. Okay, no, sorry. This I did not tell the level of indent. Okay, thank you. So temp is 0. So let's see. What would happen, Jacob, if for let's say instead of case 1 we had 6 to 4. Let's say we had 6 to 8 instead, right? So based on A and B, we still have a circle of 8 people, right? But since the C is 8, now we want to return the person standing opposite 8, which in this case is 4. Would your solution work for that?
I didn't try that. Probably not.
Okay.
Maybe.
How could we modify it to work for that? So would I think it would return 12, right? Because you're just going to add 4 to whatever C is. But it's possible that in this case we have to actually subtract 4, right? Because person 8 is on the side of the circle with the higher numbers, and so they're facing the side of the circle with the lower numbers. Right? You see what I'm saying? Why you have to subtract 4 instead of add 4?
I mean, I guess you would find the highest value of the circle
Mm-hmm.
and say that like if C is greater than half of the highest value, then do C minus temp over 2 or just the highest over 2. But if it's less than half, then you do C plus.
Wait, also, sorry, I just want to add something. It's like a very minor thing, but here you said circle size is A plus B, but it would be absolute value of A minus B times 2.
Oh, yes. Yeah. Good point. That's I was not looking at that part of the function, but you're right. Yes, that's something to keep point. Yeah. Okay. So here's the thing with sample cases that these problems give you. There might be some nice, neat mathematical properties you can find in them that may not hold true for all numbers, for all combinations of numbers. So in this case, 6 plus 2 happens to add up to 8, but that's not why the circle size is 8. Does that it make sense to you why, Jacob? Like for example, I could give you another something of the same circle, right? 7 and 3, right? They're also facing opposite each other in this circle. The circle size is still 8. But the if you were just to add up 7 plus 3, you would get 10, right? And so the reason why is because 7 and 3 are 4 opposite each other, and we know that the difference between two people who are standing opposite each other in the circle is always going to be half the circle size. Does that make sense?
Yeah, I actually end up finding the maximum value with the when I'm checking if the circle is even, I actually end up finding the maximum through a while loop. I just realized that.
Oh, I see. Interesting. Okay. By the way, I would say like also and this is not like when I say these things, it's not a critique of anyone specifically. These are just general programming rules, and I'm trying to use your code as samples to illustrate these rules. I would not put like the same variable name in both like lowercase and all caps. That could get very confusing. There are some programming languages that are not case sensitive, which means that these would actually be the same variable that you're modifying in a language like Pascal. Now, very few people are using Pascal these days, but the point is just make your code easy to read and make it clear what is temp doing, what is the purpose that it's serving. A lot of these also like the fancy like people who win all these programming competitions, right? They will like start their function with like L equals blah, R equals blah, S equals blah, and it's just like no, you've like there is no use in writing like a one letter variable name, and now you're made it harder for yourself to understand what's going on. If there's a mistake, it's harder to debug, and it's harder for other people to read the solution. I don't know. C++ programmers, they love to do this thing where they use the smallest variable name possible. Yeah, we're Python programmers. We're cool. We try to make our code actually easy to read. So yeah, I definitely at least use temp and temp2 or something like that. But even better than temp would be like using some actual like variable name if there's a more specific thing you can do. So you'll notice that sometimes in for loops, like I won't just do for I in blah blah blah, right? I'll do for IDX in blah blah blah, like index. So okay, I think Manish has this nice, and then I think Minu and Evan also had this. So yes, so this is basically we have to just essentially figure out as Jacob told us, like, hey, what side of the circle is C on? Is it on the smaller half or the larger half? If it's on the smaller half, we add the diameter. If it's on the larger half, we subtract the diameter. And I think that's it. That's all we have to do, and then we just print D. Okay. So then let's just check if this works. 4, 6, 2, 4. Should put fewer P's. What have I done here? I did not return circle size. Whoops. Okay, and so now we get 8. Thank you to everyone who helped. Evan, I'm interested in what is this C plus A minus B? Can you explain this? What is this part doing? I should.
Oh, I think what that's doing is that when it's on the bigger half of the circle, instead of doing what I did where like you subtract it from total, he was just finding the remainder instead.
I see. Okay, and so this gives us %8. Okay, yeah, it makes sense. I can see. So this is a way that also, Jacob, we could just have added this to your solution as well, where maybe you do add circle size over 2, but then if this ends up like kind of overflowing, if it goes beyond the circle, then we just we can use the modulo operator or just like subtract circle size or something in order to bring it down from like 12 to 4 in a case like 6 to 8. Does that make sense to everyone? Yes. Okay, cool. I think that is all the questions. If there are any questions on these, please let me know. Yeah, so these, I think, final 3 questions were all from Codeforces, and that's one of the competitions I had mentioned before. And then this first question was from it's called like yosupo.jp. It's a library of problems, and also like USACO participants often use these websites to practice. So these are, yes, on the simpler side, but hey, we're just starting out, and you all did a very nice job, especially considering that some of these problems are very tricky. So why don't we take a 5-minute break, maybe come back at like 7:45, and I'll just put that in the chat. Yeah. Okay, I'll see you then. Hey everyone, welcome back. Good. Can people hear me? Oh no. Hello,
Yeah,
hello?
we can hear you.
Okay, cool. There's a bit of an echo here, and I'm trying to turn it off, but I don't think I can. Okay, that's fine. Okay, cool. I hope you can see this. I'm trying to write stuff on my iPad, and yeah. Great. Okay. Okay. So there's a lot of one thing I wanted to mention, sorry, about the previous questions, by the way. Let me see if I can share my screen before I get to this. So just looking at the official solutions for these problems, by the way, what we did here, basically exactly correct. For the watermelon problem, again, also exactly correct. This is not much of an optimization, but basically what one of the sample solutions did that was slightly different from any of our solutions was it basically just calculated for A, it calculated the max of B comma C, and then it said, okay, what's the max of 0? Sorry, let's call this max BC equals this, and then max of 0 comma max of BC minus A plus 1. So similar to I think what Evan did, but basically did this for all three candidates, and this way it did like the minimum number of comparisons needed. Yeah, but ultimately it boils down to the same thing. It's not too much more efficient. Yeah, okay. So let me try to share my iPad again. Can people hear an echo? Okay, great. So it's just me. That's unfortunate, but yeah, this is not turning off the audio. Okay, great. So let's talk about sorting algorithms. So yesterday we were actually just discussing out loud, like, hey, what's a good way to sort items? But let's formalize some different ways to sort. Okay. So let's say we have a list of elements, 5, 3, 1, 1. Okay. 1, 2, 4. Okay. What's a good way to sort these things? Now, has anyone ever played the game 52 Pickup?
Yeah,
It's a great card game, right, Jacob?
it's so much fun, especially when you have to play unwillingly.
Unwilling. Okay.
Yeah.
Did you ever play with like a younger sibling or anything?
Oh yeah, I love that. I love making them play it with me.
Excellent. Anyone know what 50? Oh yeah, Manish, you have a question? You've played?
No, I haven't, but for the sorting algorithms, could we just find the max each time and then remove it from the set?
Yes, I think that's similar to what Jacob was proposing yesterday. Let's find the min each time and then like, yeah, do that. So yes, that's possible. But first I want to get to the worst sorting algorithm that you will ever see and that you should never ever use. It's called BOGO sort. So what 52 pickup is it's kind of like a tongue-in-cheek name for a game where like let's say you need to sort the cards or just pick up all the cards after a card game is done. You just throw them up in the air and then you say, hey, whoever collects all 52 cards first wins, and then you just watch as usually younger sibling races to clean up the mess you've left behind. So this is, I feel like the 52 pickup of sorting algorithms. What we could do is just put this into like a random sorting algorithm, right? And so basically we just check like we sort randomly is the first step. Then for every single element, and I'm writing in pseudocode here, not in Python, right? So for I from like, you know, 1 to n, where n is like the number of elements, you basically check, hey, does for this array x is x minus or I plus 1, is it greater than or equal to xi? And I should go to m minus 1 here. So you're just basically checking, is this in order? And if this is false, then you repeat everything, right? So you take this whole part, you can say something like this. And you can say if not this, then sorted equals false. And if at the end of all of this, if we're sorted, then break. Okay. How bad do you guys think this is? And does it make sense what's going on here, first of all? Anyways, can you explain what this is doing?
So like it's going through each of the elements and it's like checking if each element is like if like the element right next to it is greater than then then it sorts the false. But if it's not, it breaks the thing and starts all over again, I think. Yeah.
Yes. So we keep on basically randomly sorting it and then checking, hey, is it sorted? Yeah, no. Okay, let's try again. And this is basically like shuffling a deck of cards until it's fully sorted. Is there any guarantee that it will work? Like, is there like a finite time limit up until like I can say like, okay, well, after like this amount of time, everything will be fully sorted?
I mean, it could just constantly be unsorted and then be randomly more and more unsorted.
Exactly, yes. So there's no guarantee that it'll ever actually successfully be sorted. This is part of a class of algorithms called Monte Carlo algorithms. If anyone knows, like Monte Carlo is like a famous city for like casinos and gambling, and this is essentially a game of chance. If you're trying to, you know, if you're hoping for a list to be sorted at the end of this. So this is kind of just a joke sorting algorithm. No one would ever actually use this. And yeah, the expected like there's like n factorial, you know, different ways in which the list could be sorted. So it might take like n factorial different tries until you get it. That's the expected value. But of course, the upper bound for this is like infinity, because maybe your sorting randomly is actually terrible and you will never actually get the perfect sort. So yeah, I mean, like for a deck of cards, for example, 52 factorial, that's the different number of ways you can sort the total number of cards there. And I think that's more than there are atoms in the universe, which means if you think about it, every time you sort a deck of cards in a random order, it's possible that no one else in the history of humanity has ever seen a deck of cards in that sorted order before, because I mean, there's just so many different combinations. But okay, let's move on from terrible sorting algorithms onto better sorting algorithms. So you all are suggesting that we just basically go through a list multiple times and we take the minimum element, you know, each time and come up, and we just store that and then we go through the rest of the elements. I think that works, but usually I mean, not usually, for sure, like we're only like pulling out one element at a time, right? Is there any other suggestions that you guys have for maybe figuring out a way to sort elements in a list?
Maybe it could be like split the arrays based on like the smallest and largest parts.
This is interesting. Okay, this is actually a pretty good suggestion, splitting arrays. But I want to table that for later. Let's start with something simpler. And I want to point you actually to this line over here. So what does a array need for it to be sorted? Every single, let's say we're saying, I should actually define what is it mean to be sorted for our purposes. So you can define different criteria for sorting. In our case, let's say we wanted a numerically increasing order and we have like a array of numbers. So in that case, all we need to do is always make sure that for like a array of n numbers, that every number is greater than the number before it. Does that make sense? Yes, okay. So there's something called bubble sort. And the idea is essentially what we do is we check, let's say we have a list of numbers like 5, 2, 8. Oh, let me put the name of this first. Bubble sort. Clearly not sorted. What we can do is keep on going through this array of elements, and on our first pass, it will look something like this. This is what we start out with: 5, 2, 8, 12, 3. And then what we can say is for these for our first pass, or for every pass over this list, what we do is if we see two consecutive elements where they're obviously in opposite order, then we just swap them. So let's go through pass 1. Okay. So we start off by saying, okay, 5 is greater than 2, so these should be swapped. So 2, 5, 8, 12, 3 is our new modified list. And let me make clear what happened at each stage. Can I copy this? Yes. Okay. So we start off at this element over here, and then we swap. Okay. Great. Now we move on to the next element, 2, 5, 8, 12, 3. Once again, let's write this out. So is there any need to swap? No, 8 is greater than 5, so we're good. Okay, now let's move on to the next number. So 2, 5, 8, 12, 3. 12 is greater than 8, so we're good. But now we're on the last number, 2, 5, 8, 12, 3. Is there need to swap? Yes, because 3 is smaller than 12, so they should be in opposite order. So now we swap. Okay, and now we've made it to the end of the list. We're done. That's pass 1. So after just one pass, at least in this scenario, most of our numbers are kind of pretty much sorted. It's just that 3 should be over here. Okay, so let's go through the numbers again. So now pass 2, we start off with 2, 5, 8, 3, 12. We start here. There's no need to swap. Start here, no need to swap. 2, 5, 8, 3, 12. We do need to swap. So now let's swap. Okay, and now let's move on to the next one. 2, 5, 3, 8, 12. We're over here. no need to swap, and we're done. Does this make sense? Okay, let's go on to the next pass 3. No need to swap. We do need to swap. 3 is smaller than 5, so time to swap. And we shall swap by saying this. Okay. And let's check now the next number. So 8, no need to swap. No need to swap. Okay. So are we done? We are done. We know that. But how does the computer know that we're actually done? So what should the stopping condition be for this list? How do we know that we no longer have to iterate over it and make more passes? Well, basically when we make a pass over the list, if there were no swaps to be done, then we know we're done, right? Because that means every single pair of elements is sorted. Since we did swap during this pass, we're not quite done. So now we need to make one more pass. Uh-oh. My tip is okay, good. Pass 4. So 2, 3, 5, 8, 12. We start here. No swaps. 2, 3, 5, 8, 12. No swaps. 2, 3, 5, 8, 12. No swaps. 2, 3, 5, 8, 12. No swaps. So we're done sorting. Make sense? So it took 4 passes to do this. How many passes would it have taken for if we use the kind of method that Jacob or Manish were proposing, where we take one number at a time? We find the smallest number, then the second smallest number, then the third smallest number.
It would have taken 4 passes as well.
It would have
Because you only have minus of
Yeah.
them.
So it would have
Because you
taken
have the remaining.
4 passes as well, because we would be looking at the first we find the smallest number, then the second smallest number, the third smallest number, then the fourth smallest number, and then once we've arranged these first 4 numbers, well, the 5th number, there's only one option for that, so that's also already sorted. So yeah, looks good. But there are scenarios where this could have taken fewer than 4 passes. Whereas for a list of 5 numbers, I think the method that Manish and Jacob are proposing will always take 4 passes. So these are interesting. Well, why don't we though figure out a way to actually formalize it and write it in code? So why don't we take 5 minutes to write bubble sort out? Let me switch screens again. Okay. So let's say we have a list of elements. And there's n elements. What should I do to make sure this is sorted?
You could do for I in range
You should.
0 to n.
Mhm.
Oh, sorry, did I cut you off? Evan? What were you gonna say? After that, I would say if if elements I is greater is greater than elements I plus 1, then like you have them switch spots.
No, sure.
Would that be in a while loop? Because you have to keep doing it until, because you have to.
I mean, we can, or maybe we can hear you, and maybe it's just me. Wait, can people hear?
Oh, sorry, can you hear me better now?
Yes, we can hear you.
I was saying that, would that be in a while loop? Or like, wouldn't there be
Yes.
some, yeah.
Yes. Eventually, we'll put this if statement maybe nested under like another for loop or while loop. Yes, but what I think Jacob is telling us is like, okay, let's just compare elements and let's swap them. So I'll just write that part out and then we'll go back and fix the rest of that later. This is a swap. Okay, but we need to do this for every J. So we can, let's be a little lazy right now. Let's not worry about optimization. So this can stand for the number of passes, actually. Let's make this P. And this is the index that we're looking at right now. Okay, so let me return elements actually. So what was the starting example we had actually? 5, 2, 8, 12, 3. Okay, so that's not gonna work. I need to do n-1 actually. Hey, we got 2, 3, 5, 8, 12. So this works pretty well. If we want to be a little more descriptive and actually see what's going on, we could say print pass P. And then we can also print out what the list looks like at this point in time. And then here we can say print swap. And then print out what the elements looks like here. So something like this. And this is exactly what we saw on my iPad, right, where we swap 2 and 5 first. And then we swap 3 and 12. And then past 1, again, we swap 3 and 8. Past 2, we swap 3 and 5. Past 3, we do nothing. Past 4, we do nothing. In my case, I was one indexing my passes, but basically the same thing. So there's some optimizations we can make here for sure. So first of all, we can keep track of like, hey, if we haven't made any swaps this round, we're done, right? So swaps equals false. And then if we went into this, we will say swaps equals to true. And then, oops, true. And then if swaps, then just break out of this for loop. There's no need for us to continue. So this saved us a pass. Great. Now there's something else we can optimize. So the problem with bubble sort here, if you guys notice, like this 3, getting it to bubble down all the way to the actual position it should be in, which is like in an index 1, it's kind of slow. So how do we speed that up? Well, we can't really speed it up, at least in the mechanism that we have right now. But on the flip side, we do know that like, okay, while moving right to left is slow, left to right is actually pretty quick, right? Like let's say we started this list with 12. How long would it take for it to get to the front? Something like this.
One move, I mean, one pass.
One pass, right? So after one pass, we know whatever number is here in that last position, it's already sorted, right? Like we don't have to ever consider that again. Does that make sense? So I can actually do something like this, n minus p minus 1. Because I don't want to look at the last p elements. Right? So for pass 0, I'm looking at everything. But for pass 1, I'm not looking at the last element. For pass 2, I'm not looking at the last 2 elements. I know for sure that those are sorted. So now there's fewer computations I have to make. Does that make sense? And just to illustrate that better, let me print out comparing every time I make a comparison. So you can see the number of comparisons I make here versus the number of comparisons I make here, right? Way more if I don't have this optimization. Okay, so this is pretty good bubble sort. So we kind of put an upper bound on this in terms of like the number of passes we make, but also when you factor into the number of comparisons we make, right? Let's just we don't have to be very precise with our numbers, but like let's put maybe like you know an upper bound, like what is the total number of comparisons that need to be made? So first of all, what is the total number of passes we need to make if we have n elements? How many passes might we need to make? Something around 1 or n over 2, n. About how many passes do we need to make over this? Anyone? Anyone? Bueller? Bueller? Hello?
What was the question? It was something about comparing, right? Setting a maximum on that.
Yeah. So what's the maximum number of passes we need to make over this entire list?
I mean, the absolute maximum would be n minus 1.
Yes, exactly. And then how many comparisons do we make each time? Let's say we didn't have this optimization here.
So n minus 1 as well.
Yeah. So n minus 1 squared, essentially. Yeah, exactly. So I'll write that down on my iPad and then start sharing from my iPad again.
I think your thing still says n minus p minus 1.
Yeah. Sorry, I'm trying to switch to my iPad. Hold on. Right. So this will give me about n minus 1 passes, worst case scenario, and then let's say without the optimization, n minus 1 comparisons. Okay, we could get more precise than that, but let's not. Okay, so we talked then, I think you guys were mentioning insertion sort. This is actually the sorting algorithm that Manish and Jacob came up with. So let's start off with, again, maybe the same list. I need to remember what these are. 5, 2, 8, 12, 3. Okay, 5, 2, 8, 12, 3. Okay, so what do we want to do? So there's two ways of doing this. One is like, let's create like a new structure in memory where we basically go through this list once and then we say, okay, pass 1, the smallest number is 2, right? And then we inside of this newly allocated list we have 2, and then everything else is still blank, right? And then maybe we make a second pass through this and we say pass 2, 3, pass 3, 5, pass 4, 8, pass 5, 12, and after each pass we are slowly like adding stuff to this place in memory. This works, but the thing is, it's more convenient to not have to allocate a separate, memory structure. You want to separate, like, create a new data structure, like allocate a separate buffer of memory if you don't need to. So let's just do things in place. Let's use this same array that we have here and sort things in place. Okay, so pass 1. What are we doing? We're checking, is 5 the smallest? So far it is. Let me, oops, let's move this out. Okay. So smallest so far is 5, right? Then we move on to 2. So far the smallest we've seen is 2. So far the smallest we've seen is 8. So far or no, it's not 8, it's still 2. Right, then this is still 2, and then this is, let me try to look deeper. Okay. And then finally, the smallest number that we've seen so far is 2. So let's say we were keeping track of that index, right? So we know that 2 is the smallest. So it should be at the start of the array. So then whatever is at the start of the array, we don't want to delete it from the array. So we just swap it, right? So we can say, okay, well, pass 1 is done. Time for a swap. We're going to say 2, 5, 8, 12, 3. Looks good, right? Okay. Now what's next? Anyone? Manish? What's pass 2 look like? Wait, am I not sharing my screen?
No, we can see it.
Okay, I can't see it. Interesting.
Okay. I'm not sure.
Do people understand what's going on here?
Wait, you're asking what the second pass is gonna look like?
Yeah.
Well, the 3 gets moved down again.
Sure. Right. So we no longer have to look at the first element, which is 2, right? But we can look at 5 and say, okay, so far that's the smallest. Now we look at 8, well, 5's still the smallest. 12, 5's still the smallest. 3, oh, hey, 3's the smallest now. Okay, well, we're done looking at the entire list. Time for a swap. And so now we do 2, 3, 5. There's 2, so 2, 3, 8, 12, 5. Excellent. So now pass 3 looks like this. We know that this is sorted, right? So now we only have to look at the final 3 elements and we say, hey, is 8 the smallest so far that we see? 8's still the smallest. Oh, 5 is the smallest. So now let's swap 5 and 8. So something like this. Great. And now time for our final pass through this. We say, hey, these are the final 2 elements, 12 and 8. What's the smallest? Well, 12 is the smallest when we go over that, but now when we move on to 8, we say, oh, 8's the smallest. Okay, swap again. And since there's only 1 element left, we can actually stop here because we know that that's sorted. So that's it. Does that look good? Insertion sort? Is this, what you guys were thinking of, Manish, Jacob, when you proposed a sorting method?
Yeah.
Kind of.
Yeah. Kind of.
Yeah. Okay, nice. So this is also like, you know, a good sorting algorithm. Let's try coding it up. Try this insertion sort. Okay, what do we want to do here? For let's say we have number of passes again. Let's okay. So how should we go about doing this? Well, for each step, basically what we have to check is, okay, what's the index of the smallest element? So let's say, okay, for index in range, and we want to start at 0 for the first pass, 1 for the next pass, second for the third pass. So we want to start at P, basically, whatever is the pass number. And then we want to go until the end of the list. So P to N, right? And then we check what's the smallest number seen so far. So let's initialize smallest to none. Smallest num. And then we also need to keep track of the index of that smallest number. So if smallest num equals or sorry, wait, there's something in the chat. Use the min function and iterate. No, you can use the min function, but the thing is the min function is kind of like abstracting, like you're obscuring what's actually going on behind the scenes, and you also won't get the index of the minimum value. So we need to do this manually, kind of going through each one. Now, are there better ways to do this? For sure, but this is just for illustrative purposes. If I wanted to write like very nice compact code, there's fancier ways to do this. But right now I just want to make it very, very blatant what is happening. So if smallest num is not defined, basically. So if not smallest num, or this is not great. Let's just initialize this -1. Let's pretend we know that for sure that all of our numbers are all positive. So if smallest num is not is equal to -1, then we need to set what our current number is, which is elements index and smallest index. So this is equal to index here, right? Otherwise, if we have initialized them, then what we have to do is say smallest. We only want to change the smallest num and smallest index if we found a smaller number. So if elements index is smaller than our current smallest num that we've seen so far, then we update smallest num and smallest index. Does this make sense? And so at the end of this for loop, we should be left with what the smallest number is and the index of that smallest number. And so now we can then just swap and say, okay, elements P, comma, elements smallest index is equal to elements smallest index, comma, elements P. And so we swap. I can print out comparing each time, and I can print out what it looks like. Well, we don't have to print out what it looks like after a swap because we'll just see that on the next pass because we're just making one swap. Okay. Now let's try sorting this. Okay. This looks good to people. Yes. Does it make sense what's going on here? Okay, now let's try to put a bound on this as well. What's the worst case scenario? How many passes will we have to make according to this? N, right? Basically, we're making N passes. And then here, how many elements are we looking at? Technically, it decreases each time, but basically it's something like up to N. So yeah, technically it's n minus p, but let's just say it's up to n. So this is about like n passes and n elements each pass. So it's about like n squared total elements that we're looking at. Similar to bubble sort in the worst case scenario. However, in bubble sort, we can terminate it early, right? Because if we see everything is already sorted to begin with, we're done. The way we've written insertion sort right now, we don't have that option. So if we want to make it a little faster, one thing we can just check, we could have done is say something like, hey, if list is sorted, break. Which means though then that we have to check if the list is sorted each time at the end of a pass. So that does take more time, but it could allow us to finish everything early. Does this make sense? Bubble sort and insertion sort, how these two work. Okay. Now, this is going to be the trickiest one we have dealt with so far. Let me share my screen. Okay, merge sort. Okay, so let's start with a longer list actually, so that it's easier for me to illustrate what's going on here. Okay, so we have a list of 8 elements. Wait, am I still sharing? No, I'm not sharing, am I? Am I sharing my iPad? No. Okay. Okay, am I sharing my iPad now? Cool. Merge sort. Okay. So here what we have is a list of 8 elements. It's not quite sorted. Well, we want to be able to sort it. So I think Manish had said something about splitting things into smaller arrays or something like that. This is an interesting idea. Let's explore this. So we have a array of 8 items, right? Let's break this down into smaller arrays. So first, let's make this an array of 4 items over here, and then an array of 4 items over here. But actually, we can make it even smaller than this. Right, so 4 arrays of 2 items. Actually, we can even make it smaller than this. So let's make it 8 arrays of 1 item. Anirudh, do you see anything interesting about the way that we're subdividing this problem? Any familiar concepts here? Any self-similarity that you see in this? Any kind of keywords that you might remember from yesterday that you want to mention? What does this remind you of?
It's kind of like breaking it into like tuples.
Well, did you remember what we were covering yesterday when we were
Cut it in half.
That's the watermelon question.
not the watermelon question, but when we were doing, for example, the Fibonacci sequence or the palindrome by breaking it into smaller.
Oh, recursion.
Yeah, recursion, right? So there's some kind of recursive element to this so far, right? We're just splitting things into smaller arrays. And then we've reached this base case. This is the smallest we can go. So we have 8 arrays here, right? Yes, exactly. So we have 8 arrays here. And are they all sorted, each of these individual arrays? Are each of these arrays sorted? Anyone? Is this array with just a single element in it? Are all the elements in here sorted?
Yeah.
Yeah, technically.
Yes. So we have 8 separate arrays, just to be clear. But within each array, all the elements are sorted. So we're done, right? we're not done. We're not done. But this is our base case. We want to basically make an algorithm that looks something like this. The pseudocode is, okay, let's split it in half. And basically you repeat until you get to arrays of size 1. Okay. Then you sort what's in the array. And then you merge it with the next array.
How do you know which order to merge it in?
We'll go through that. This is a good question. I'm being a little like loosey-goosey with the wording, but there's a more explicit way to write it, which I'll do later. So then we'll sort again. And now that the like arrays are sorted, it's easier to sort the larger array as well. Okay, and then you keep merging until you have one array. Okay, so that's the general what the algorithm looks like. Okay, so we have 8 arrays, they're each sorting. Now let's go back and merge. So the way we're merging is basically in pairs and exactly like the way we split it, we're just reversing that process. So hopefully that makes sense, Jacob, how we're merging. So we merge and we get something like this: 5, 2, 8, 12, 4, 6, 3, 7. So this is where the previous arrays started. So back when we had just arrays of 1, right? This how do I phrase this exactly? So we have arrays of 2, length 2 here, right? 2, 4. Okay. So both 5 and 2 were the starting points of the respective arrays they came from. 8 and 12 were the starting points of the respective arrays they came from. 4 and 6, same thing. 3 and 7, the same thing, right? So all we have to do for this step is basically sort these arrays of 2. So 5 and 2, it's very easy to sort that. 2, 5, right? 8, 12 is already sorted. 4, 6, 3, 7. So now we're left with 4 arrays of length 2 that are each sorted. Okay, so time to merge again. So now we have arrays of length 4. So 2, 5, 8, 12, 4, 6, 3, 7. So now these were the previous starting points of the arrays, right? So back when we had arrays of length 2, 2 and 8 were the starting points of their arrays, when 4 and 3 were the starting points of these arrays. So that's where I put these arrows. Does this make sense? It feels like very few people's eyes are on the screen. I don't know if people are following along. Okay. Does this make sense where we are right now? Okay, it makes sense to Evan. But Evan's eyes were on the screen, so I was okay. Jacob says yes. Minu, yes. Manish, Anirudh. And oh, we have another student in this class. I think Bagheerath, is that right? No, okay, that's just me. Twice. Okay, so come on. People are too tired to laugh at that lame of a joke. Wow, okay. I see how it is.
No, it's
Yeah.
just it wasn't funny.
Okay. That's fair. That's fair. As long as you're listening. So we have 2, 8, 4, 3. These are the 4 starting points of the previous arrays. So now what we can do is, because we know that, like, okay, everything from 2 and 5, right? This thing is sorted within itself. This thing is sorted within itself. This thing sorted within itself. This thing sorted within itself. So we don't have to completely go back and recreate the wheel and sort everything from scratch. What we actually have to do for sorting an array like 2, 5, 8, and 12 is this. Actually, 2, 5, 8, and 12 is already sorted, so that's maybe not an easy example for me to demonstrate on. Let me try 4, 6, 3, 7. Okay, so 4, 6, 3, 7. Let's say we're going to allocate like a new space of memory for this. So the two subarrays that these came from, 4 and 6, 3 and 7, right? What is going to be the smallest element in this new array? It's either going to be 4 or it's going to be 3, right? There's no way it could be 6 or 7 because we already know, because these subarrays were sorted, right, that 4 is smaller than 6 and 3 is smaller than 7. Does that make sense? So in order to figure out what the smallest element is of this new array that I'm creating, I only have to look at these two elements. So in this case, I only look at 3. Great. And now that I've already looked at 3 and added it in my new array, I don't have to ever look at it again. And so let me just move this pointer here to 7. Great. So now we have 4 and 7. What's the smallest of these two elements? It's 4. Great. Now I never have to look at 4 again. Now let's compare 6 and 7. What's the smallest of this? So we compare these two and we are left with, we have 6. And now we're done with this array. So now we only have 7 left. And we put 7 here. Does that make sense how we sorted it? But this took a lot fewer comparisons than bubble sort or insertion sort would have used, because we have pre-sorted arrays. Great. So now we sort and we have 3, 4, 6, 7, 2, 5, 8, 12. And this is sorted. Now finally we need to merge one last time and we have one large array. 3, 4, 6, 7. Okay. Why don't you all help me figure out how to sort this one? What are the two comparators and points for this large array? Well, we start where the smaller arrays of length 4 started. So 2 and 3. Anirudh, what do I do? How do I start this off?
Well, probably you could split it into 2 arrays first.
We've already split it into 2 arrays, right? Now we're merging together. So we have
Oh yeah.
we have size 8 now.
So then probably you could swap like the next like 2 like surroundings, like you can compare 2 and 5 first, and since 2 is less than 5, it stays there, and then you can keep moving up the ladder, like up the array.
Yes, exactly.
Wait,
So-
if I may interject, I think we already know, because it was in a previous array, that 2 is less than 5. So you would just need to go up the amount of the length that the previous list was and compare 2 and 3, then compare 5 and 4, and so on.
Yes. So what you were saying about like comparing halves of arrays, I think that's correct. But like the specific numbers, I think not 2 and 5, it's 2 and 3. So yeah, as Jacob said. So because this came from one array and this came from another array, right? We only need to compare the starting points of these two arrays because one of these will be the smallest of the final array. So in this case, we compare 2 and 3. So 2 is the smallest. Great. So now we move on. What? Wait, sorry, I don't know what's going on in the chat. What was not to, Jacob?
Because he didn't compare 4 and 8.
Oh, I see. It's in reply to Evan. Okay, sure. Okay.
Yeah, because if you do 5 and 4, then you have to compare 4 and 5 before going to 8 and 6.
Oh, okay, sure. We'll get there. We'll get there. Yeah. So 3 and 5. Now we have to compare, right? Because we're already taken out 2. So now 3 and 5. What's smaller from these two? It's 3. Great. And so let's cross this out. And what's smaller from 4 and 5? It's 4. Great. Let's cross this out and move on the pointer over here. What's smaller from 5 and 6? It's 5. Great. Let's cross this out and move the pointer. What's smaller from 6 and 8? It's 6. Great. Cross it out, move the pointer. What's smaller from between 7 and 8? It's 7. Cross it out. And now there's no more pointers, and we can just append the rest of the list from here. 8 and 12. Does this make sense? Cool. So this is a lot more steps and thinking, and maybe not like the most intuitive sorting algorithm. So why would we do something like this? The only reason why
Speed.
speed, exactly. The only reason why you do complicated things in computer science, speed. For whatever reason, and actually we will explain what reason in a bit, but for whatever reason, this is the faster algorithm. And but let's actually maybe before we like formalize it, let's just think about it out loud. What made this faster sorting wise? Why was it a bit faster to do?
We split it like into smaller groups. So since it's smaller groups, it's easier to sort.
Yes, so the smaller groups are easier to sort, but then we have to put the groups back together, right? So we have large groups again. So why does it help that we have already sorted the smaller groups?
I guess
Because-
because in the larger group, oh, you can go ahead.
Oh, sorry, no, it's fine. You're okay. I was just gonna say because each half was already sorted.
Yeah, is that what you were about to say, Anirudh?
Yeah.
Okay, good. Yeah, so now each half is already sorted, so it's easier to compare because we don't have to compare everything. We just have to compare the start of each array and then like move on downwards. Cool. Why don't, let me think. Actually, before we take a break, why don't we implement this in code? And then we can take a break. Second. There. Okay. So there's a few ways we could do this. But we could do this with recursion, right? Okay. So first, let's assume for now that our array is exactly a power of 2, right? So it's a length 8 or something like that, or length 4, length 16. We'll just make our lives easier. What does our base case look like in this case?
If the length of array is equal to 1.
Right. So if len of array equals 1, return array. Right, because it's sorted. We could even just make it less than or equal to 1. I don't know, for whatever, if for whatever reason, if for whatever reason our length of our array was 0, it's also already sorted. Okay, now what does our recursive case look like? Someone besides Minu or Evan. Manish? Are you saying something? Actually, I can't hear you.
No,
So there were 2 parts of merge sort, right? Well, first we split things. We sort the subarrays, and then we merge together the sorted arrays. So the recursive case, and this might be a little complicated since we didn't quite do a recursion problem like this. So there's some pre-work. We call the function on itself recursively, right? And then there's some post-work. So first, let's do split. Then call merge sort on each split array. So this is the recursive call. and then merge. Does this make sense? Okay, so it's a bit like a tree if you think about it. So one, I'm trying to think what's the best way for me to do this. Let's start with, okay, let me just make let's pretend it's already sorted, but 6, 7, 8. Okay, and then the layers of the tree, it's something like 1, 2, 3, 4, 5, 6, 7, 8. And then this is 1, 2, 3, 4. And then this is 1 and 2. Okay. I'm not gonna draw the rest of the tree out, but I think you guys understand what it would look like. So this is our initial function call. We first split, and then we call merge sort on this, and it does the same process, right? Split, merge sort, split, merge sort. Then it merges the list and sorts from there. Merges the list, sorts from there, merges the list, sorts from there, merges the list, sorts from there. So does that make sense how like we were breaking it down and then we're putting it back together? And the way recursion works, right? Like our first call is going to break it down from a length of list, a list of length 8 to 2 lists of length 4. And then we let just merge sort take care of itself because it's doing stuff recursively behind the scenes, okay? Then when that function call returns, we're back with 2 lists of length 4, and all we have to do is merge at the end, list of length 8. So it looks a little something like 8, 4, 2, 1 when it comes to the length of the list, and then it merges together to 2. This is 4. This is 8. Now, this is actually part of the same function call. This is part of the same function call. This is part of the same function call, right? And this is one function call. But so what's going on here is first we break the list into 2 subarrays and we call merge sort. Once merge sort here returns in line 6, right? We put things together. I'm trying to say the same thing in multiple ways just to kind of help clarify like how we're coming up with this design. Does it make sense to people? Right? So the same function call in which we split the list is later on where we merge the list. It's happening in reverse order though, because first we go down and break it down until it's smaller size, and then we build it back up until it's a larger size. So this is like the first place where we call the function. This is also like the last place where it returns. Does that make sense? Okay, let me clear all the annotations off my screen because it's getting messy. But okay, so we have 3 steps: split, call, merge, sort on each split array, and merge. Okay, so Manish, can you help me split this up, please? Split these 2 arrays.
Okay, yeah. So wait, so which 2 arrays?
Or split like the array into 2 arrays.
Oh, okay. Yeah, sorry. Um,
Let's rename this element. Let's just, yeah, okay. Let's just stay consistent.
okay, so we probably should create like elements 1 and elements 2.
Mhm. Okay, and what is elements 1?
Well, since we're splitting it into half, it would probably be the index of 0 to elements divided by 2.
Mm-hmm.
And then for elements 2, it would be elements with the index of len elements over 2 to len elements.
Okay, to the end, yeah. And This is optional because it automatically goes to the end of the list and automatically starts at the start of the list. So I don't technically need these, but I can leave them in for clarity. Okay. Does this make sense to everyone? Okay, now what do? We call merge sort on each of these split arrays. This is hopefully the easiest step. Someone help me with this. Evan, tell me what we're doing. I think you might have put this in the chat, but yeah, you use colons. But what do we do? How do we call merge sort on this?
Just say merge sort elements 1 and with elements 2, right?
Yeah.
So you say. So you say that that's equal to elements. You said elements 1 equal to that, and elements 2 equal to the other one.
Yeah, good. We could do something where we maybe sort it in place, but let's just make our lives easier, create a new list and return that list each time. So every time we call merge sort, we should stay consistent between the base case and the recursive case. Both of them should be returning some list, whether or not that's a new list. And does that make sense to people? What's going on? Okay, cool. So we have two lists here that are being returned. Okay, now this is the tricky step, the merging step. How do we do this? Anirudh or Minu?
Could you use the append function? Or is that for strings? I forgot.
You can use the append function. It's going to append one element at a time. So do you want to? We can do that. We can create a new array, like new elements equals blank list, and then we append each step one element to this. And we have to pull that element either from elements 1 or elements 2. But how do we do this? What's our procedure?
Probably adding the lists together, maybe.
Well, if we just do elements 1 plus elements 2, both these lists are sorted within themselves individually, but the overall thing.
Okay.
So what should we do?
Well, I'm not too sure what function can both like merge them together and also automatically. Wait, do we use like merge sort sort again, or
Well, we already used merge sort here. So we split it, we merge sort. So each of these sub arrays are sorted, and now we're merging.
yeah, I'm not too sure.
Okay, Minu?
I don't really understand either.
Okay. Do people, it's fine if you don't understand how to translate this to code, but do you understand what step is actually even being done in this merging process? In this merging?
It's like when you have those individual like lists and then you're combining it into lists of 2 and then 4 and then 8, right?
Yeah. So let's say we have a list of we have two lists of 2, let's say, and we're trying to combine it into a list of 4. Right. So that's what this step is. And the question is, how do we do it? So let me help you all out because I know, again, this is the first time seeing it. It might be a bit tricky. So there's a pointer to the start of the array for both of these arrays. We should be keeping track of that so we know like at which place in the array we are. So let's start with that. So let's say index 1 equals 0, index 2 equals 0. Okay. And so what we should do is, and we probably do this in some kind of like while loop. We keep doing this until like index 1 or index 2 has reached the end of their respective lists. But let's worry about this condition later. So what do we want to do? We want to compare the element at index 1 for elements 1. And the element at index 2 for elements 2. Okay. If elements 1, index 1 is smaller on your, what do we want to do with that?
Sort it so that elements 1 goes to the front of the list.
Well, I mean, we're looking at a single element at a time. So it's not that we're like this whole thing is a sorting algorithm. We're not sorting a single element though. What we want to do is, yeah, sure, we want to pull that first element out, whatever's the smaller of the two elements, we want to pull it out and put it, you know, maybe at the start of new elements, let's say. So
Can't you use the insert function? Like insert index 2 into index 1.
insert index 2 into index 1. Can you explain?
Like sorry, you insert elements to index 2 into the elements 1 list, but like in index 1 plus 1. So like ahead of it.
I see. Yes, you could do this. I will later talk about why we may not want to do such a thing. This is and let's also keep it simple now. Let's so I while you were gone, Anirudh had mentioned, like, why don't we create a new list and then we just keep on appending each element that belongs in that list next to it. So we're just going to use the append function. But how do we know which of these elements to append? Which one should we be appending from these sublists?
So we have
So sorry, good. Oh, okay. So okay, we split things into two arrays, right? Elements 1 and elements 2. So let's say that elements is of length 8. Then these are each of length 4. These are now sorted and length 4. And now, while these subarrays are sorted, we want to combine them together so that they're, you know, fully sorted, the whole overall thing. And so the way we do that is we take it's unfortunately hard for me to share my iPad and this at the same time, but let me try annotating my screen. So if you remember when we had our pointers, right? Pointers are just these arrows are just basically indices, right? And so we just compare the indices, the smallest indices we have for each array. And once we figure out what the smaller is of these two elements are, we add that to our list. We, for example, might go and take this and add this to our big list. And we increment our index. So now our pointer will, or index will point here instead. Okay, so we want to do that exact same process here. So if elements 1, index 1 is the smaller of the two elements, let's add that element to our list. And then in the meantime, we can also say index 1, let's just increment that by 1 so that this pointer gets moved. Now, if this element is not smaller than this other element, then we want to do the opposite thing. We want to increment the other element, right? Does that make sense to people? Okay. So this if-else thing is working for us right now. And it's constantly going to increment the smaller of the two elements. And then it will increment the index. Or sorry, I think I said increment twice. It's constantly going to append the smaller of the two elements from these two lists that we're looking at, and it's going to increment the index. So we keep moving along. Now we want to keep chugging along as long as it makes sense to keep chugging along. We can't go past the end of the list. So what we want to say is while index 1 is less than the len of elements 1, and index 2 is less than len of elements 2. Okay. So once one of these reaches to the end of the list, we don't have to compare to a list anymore. We're done comparing. We just take the rest of the next list and just slap that onto the end of new elements. So once we've broken out of this while loop, maybe we have an example that looks something like 1, 2, 4, 6. Sorry, 4, 5, and then this is something like 3, 6, 7, 8. All right. We look at this and this, right? We add the 1, and then we move this down. Okay, so then we're comparing the 2 and the 3. We add the 2, and then we move this down. And then we add the 3, and we move this down. Then we add the 4 after comparing 4 and 6, and we move this down. Then we add the 5. Okay, but now we've finished the while loop. Okay, but these 3 elements still haven't been assigned. It's very simple what we have to do, right? Basically, whichever index has not reached the end of the list, we know the remaining elements of that list need to be just appended to the overall final list. Make sense? Okay. I see some nods, so I'm hoping that makes sense. Okay, so what I'm going to say is, hey, so if the reason why we broke out of this while loop is because it's index 2 that had finished the list, then that means we just want to append the rest of index 1 to this. So we can just say new elements plus equals just the rest of this list. Okay. On the other hand, if we broke out because index 1 had reached the end of the list, then what we want to do is append the rest of elements 2. Or not append, sorry, add. So the way append works is you add a single element at a time, plus equals will add like a list at a time. That list may just have a single element in it, but basically this takes in list at the end, and this takes in a single number. Does that make sense? This is looking to append each one element at a time. This is looking to append like list of elements or tuples of elements or something like that. Okay. So now this is fully sorted at the end. So we can just return new elements. And we're done. So now actually let's try this. I'm excited to see, does this work or not? Hold on, my screen just flickered and died. Okay, back. Oops. Okay, what's happening here? Slice indices must be integers or none or have what? I don't even know what that means. Okay, it should be //2. Yeah, because /2 would return a float. Okay, so then it just needs to be /2 so it returns an integer. But hey, that's sorted. Does it make sense to people how this works? Okay, cool. I think that's pretty good work, and it's time for another break. Why don't we take a longer break since people seem a little tired? So maybe 9, 11, that's 9, 12 Pacific. Let's take a break until then. Yep. Is everyone back? Minu, are you back? We're gonna hope she's back. Okay, so I have a question. How much of this is making sense to people? If I asked you to implement this from scratch yourselves, would you be able to do it?
And I understood like the concept of it, but the merge sorting, the way that you coded it, I feel like I couldn't replicate it. Like I understood it when you wrote it, but like I couldn't replicate it on my own.
Okay,
No, I understand, but I need to practice it though.
I think that's fair. Okay, fine. Are people, do you think do you feel familiar enough with arrays and different data structures like dictionaries, things like that? Yes, okay. I think I'll go through it anyway, just just to maybe like make sure it's really hammered in. Where was this? Okay. Let me share my screen. Okay. So how do you create an array? Basically, there's a few ways to do it. I mean, you could just say, hey, numbers equals to blank, right? You could also, though, do something like this, where you create an integer array with the size of 5. So you just create 5 slots. And just initialize it with 0. So this is what this is going to actually create under the hood is numbers equals to 0, 0, 0, 0, 0. Or you could just create and initialize it with actual, real values, not just garbage values here. Right. If you want to add elements to an array, you could do numbers.append 6. If you want to add an entire separate array and just add the elements there, you could do numbers is 2, 3, something like that. So let me try running these so you guys can see the results of this. And then, oops, let's print numbers. So this is, let me, okay, let's say I were to do numbers dot append 2, 3. Does anyone want to guess what would happen? Or anyone know what would happen?
What do you get in brackets?
Yeah, so now the list itself will become an element. So do you see the difference between this and this notation? Because this is considered as a a single element. Anytime you use the append function, you're using a single element, right? The list itself becomes an element. Okay. Now, if you want to remove elements from an array, it's as easy as using del. You could also use remove to remove a specific value, and it'll remove this first occurrence. Of course, I've removed 2, and that was where numbers 1. So I should probably remove something else like 6. Okay. And then I'm left with just 2, 3. Because I called this part twice, so that deleted 2 first, and then 3, and then this call deleted 6. Okay. Does it make sense how this delete and remove work? Okay. One thing I want you all to think about is what is actually happening when you delete an element or remove an element. So let's say I'm gonna try annotating my screen again. Let's say I have some array like 0, 4, 6. Can people see this color? I can barely see this color. Let's look at something nice, like a nice, that's not nice. Dark green. Okay, sure. Okay, so I'm going to delete the 0. What actually has to happen internally? what will happen if I delete the 0, right? Either I do delete number 0, or let's make this 7. Okay, let's delete numbers 0 or numbers dot removes 7. Either way, it's going to do pretty much the same thing of deleting this, right? But what happens? What's going to be the final result? It's going to be look like something like this: 4, 6, 5, 1. So what does the computer have to do to get from here to here?
Remove the element, then create like basically recreate the list.
Yeah, so it could create a completely separate list with this 7 removed and return just 4, 6, 5, 1 to you. It could return the same list in place, but in order to return the same list in place, what does it have to do with 4, 6, 5, 1?
It has to shift them so that the indices match up.
It has to shift them, exactly. So what happens is, okay, we remove the 7, great, so we're left with this. But now everything needs to be shifted left. So first we move the 4 over. Then we move the 6 over. Right. And you can kind of, imagine what happened, everything else. 4, 6, 5, 1. We shift everything over, and then we just shrink the bounds of the list. And so there's no comma X at the end of it, it's just 4 elements. Now, let's say I were to do the same thing with the same list, except instead of deleting number 0, I'm deleting numbers 4. Let me move this up. I'm deleting numbers 4, or just numbers that remove 1. How long does that take? Or so not how long does that take? What operations does that take?
It moves the every like 6, 5, and 1. It moves those indices.
Do you have to move any?
It doesn't have to move any indices because no,
Yeah.
because it's the 4th one. I mean, because it's the last thing, right?
Exactly.
Right.
Would you agree, Anirudh?
So last thing it just turns into next.
Does this make sense, Anirudh, that like we don't have to move anything in this case? Sure. Okay, so what do you think is faster for the computer to do? Remove something at the start of the list or something at the end of the list?
Something
At
at
the
the
end.
end.
Something at the end, right? Because it barely has to do any work. It just has to like note down kind of internally, like, oh, okay, now like the boundary of the list has shifted. We shouldn't be accessing this 4th element anymore. But that's it. Nothing's changed in terms of like shifting. So this takes a lot more time to move around things than this. And this is kind of sometimes the problem because Python has these high level abstractions, right? These fancy functions that do a lot of things under the hood. Not that C++ doesn't, but Python especially has these things. The time it takes, the computations actually that are happening under the hood get obscured. And so it's important to think about like, okay, when I'm doing something, like how long does it actually take? So when you create a new array from scratch, that takes time because you're allocating new space. When you're adding things, so I think you had mentioned inserting things, Jacob. So when I insert a 2 into the middle of this list, let's say, right? What has to happen to the 4, 6, 5, and 1?
They have to move to the right.
They have to move to the right. Yeah. Now, if I insert something at the end of this list, like a 3, what has to happen?
Nothing.
Yeah, not much, right? Now I can give a little more background about what is actually happening inside the list. So a list has internal information that's not kind of exposed to you, but kind of is part of the implementation in Python. It basically is allocated maybe a space of like 100 elements, right? The list might actually only be 1 element, or it might be 0 elements, it could be 5 elements, but maybe it's allocated a space for 100 elements. So anytime you have to add like a 6th element, a 7th element, an 8th element, it just kind of has a space allocated for 100 elements. and it notes that, okay, the first 6 elements are actually valid, maybe if there's 6 elements, right? And it just puts this element that they've added in slot 6, or I guess there's 7 now, but or no, it is slot 6, because we're doing 1 index or 0 indexing, yeah. So slot 6, we just added 3, and we just know that the length of the list is 6. That's all we have to change. Now, what happens when we add our 101st element, let's say? Or no. Yeah, let's say we put, so, okay, we have elements in slots 0 to 6. What happens if I add something to slot 100, right? Well, the buffer for the list had 100 spaces in it. So now this is saying like, okay, I need like some like 101st space, right? Do we have enough space for this in the list? Anyone? Python has said like, okay, I'm allocating like 100 spaces here. You filled up slot 0 through 99. Now you're putting something in slot 100. Will this work?
Well, yeah, because there's still an open slot.
So remember, we're 0 indexing, right?
Oh, you meant okay. No.
Yeah, sorry. I know it's confused, so I was trying to be clear with the syntax, but yeah, so slots 0 through 99 are filled, so that's 100 things that have already been added to this list. We had behind the scenes allocated 100 spaces for this list, but now we're using up all of them. What happens when you append? You're adding something to slot 100 now, which is the 101st element.
Would it get
Would it
rid of
be-
like one of the first elements?
Would be like equivalent to like the replace function, replacing the last one.
So let me ask you guys a question. You're Guido von Rossum, okay? The designer of Python, the benevolent, what is his name? Benevolent dictator for life, right? That's what they call him, right? He's the guy who, until he like retired like a few years ago, he basically determined everything that happened in Python because he was the creator of it. Do you think it makes sense to have this kind of behavior in a language where like, okay, suddenly you added too many elements to a list, so we'll just chuck some of them out? We'll just drop some of them.
Wait, does it just increase the buffer?
It just increases the buffer. Exactly. Yes. So it's just going to allocate more space for it. Right. And now it's going to have the buffer for the list is 200. Okay. And so now we have space again. Great. But what happens between this and this? What's actually happening is that it takes time for the code to, for the computer to allocate now a new memory region and also make sure that, or maybe append more memory to your existing memory region, but whatever it is, it takes time for you to have that, space added. So if you were to time like how long it took to add a number to the list, right? Let's say you add 100 elements in that initially like allocated buffer, that buffer that was initially given to you. The first 100 elements you add, or sorry, when you have that first element, it might take a while, right? Because you first have to allocate a buffer, right? But the next 99 elements won't take as long. But now when you're adding the 101st element, it's going to take a longer time just because the buffer for this list needs to increase in size. So this is sometimes important to think about when you're trying to design code as quickly as possible. The thing is, for algorithms, it usually doesn't matter because algorithms aren't about like, these kinds of understanding the systems, right? It's not about like, okay, how does this particular system work? It's just in general, how does the code operate? But if you are looking for like a holistic solution, like how do we make things as fast as possible, this kind of stuff matters. Okay, so now let's go on to updating elements in an array. Hopefully this syntax makes sense to you. It's indexing, and indexing can allow you to both get and set values. Right, so you can say number 0 equals to 10, and that will reset it. But if there was no number 0 in the list before, what will happen? let's say we had empty list numbers. This doesn't work, right? Because you're trying to update the value of an element at an index that doesn't exist. So you need to make sure that something existed in that 0th index before you replace it. Okay, so if you want to access it, it's the same kind of notation, this indexing notation. And then to loop over it, you can loop, using the for loop. Getting the length of an array is just as simple as using len. And yeah, that's pretty much it. I think we've gone over the rest of this, these string stuff. But there are other string functions that maybe you guys should know, and I heard you mentioning some of them. So for example, the replace function will find the earliest, or not the earliest. So it'll find like every occurrence of this first substring and replace it with the second substring. So if I were to run this, new text will give us this. I like docs, but some people prefer docs, which doesn't make sense, but that's what this code does. So it's important to recognize, like, okay, does a function edit something in place? Or does it create a new copy and return a new value? Now, for most string functions, it's almost always going to create a new copy because strings are immutable. They can't be edited in place. So you don't even have to look it up. But for other functions, like for things modifying a list, yeah, you should probably look it up. Okay. String.find is also important, function to know. Like it'll find the earliest occurrence of something, like starting from the left. But again, this kind of obscures to you what is going on under the hood. If it could take a long time for string.find to work if you have a very long string and that substring that you're looking for is at the end of the list. So if you know it's at the end of the list, though, you can just basically start from the end. There's an rfind function, which will return the rightmost occurrence of a substring for you, or you can just implement it yourself. Okay. If you have a multi-dimensional list, right, 2D array or 2D lists, to access an element in a 2D array, first you have to figure out, like, okay, which is the innermost list that I want to first access. So if it's first this 1, 2, 3, that's what this first 0 does. And the second 0 will find the 0th element in this. So that's 1. And then for matrix 1 and 2, right, it's going then to find this, which is this. This is the first list, and they're using 0 indexing. And then the second element, again using 0 indexing, is 6. And if you want to modify an element, right, you can change this to be 0. So this 5 will be replaced with the 0. Okay. Does that make sense? I saw the story about a programmer who, I mean, he had just gotten into programming and he just loved it absolutely. And he loved creating lists and arrays and stuff like that. And one time his girlfriend said to him, like, hey, sometimes I feel like you love programming more than you love me. And he said, look, if I were going to create a list of all the things I love most in the world, don't worry, you'd be at index 1. Jacob laughed. Jacob, I got you. There we go. Okay.
Oh, you don't have to call me out like that.
No, I just my goal of every day is to make you laugh. That's it. Anirudh smiled. I could not see Minu because her camera was off. Manish is always smiling. I think Evan's also usually smiling. There we go. I am happy. We can end class right now. No. Okay. So one thing to know about this is, like, oftentimes, like, if you want to arrange elements in like rows and columns, right? Let's kind of actually rearrange this matrix to make it nice looking. Okay. So what is the row here? So this is the row, this is a row, this is a row, and then 1, 4, 7, 2, 5, 8, 3, 6, 9, this is the column. So in order to access it, if you're thinking of this as like coordinates in like a 2-dimensional, like, I don't know, plane or something like that, the first element is the row, the second element is the column. But yeah, okay, let's just leave it there. And so cubes, yeah, you can extend it to 3-dimensional arrays as well. Okay, let me just stop there. I think this is good. I will give you guys some homework, maybe with string and array manipulation maybe some recursion stuff as well. Okay. What do we have to go over now? I think we can and should have enough time to go over new material, and then I'll just assign you guys homework that hopefully won't be too difficult. Or what we could do is go over dictionaries and sets and other data structures. Do you guys want to go over dictionaries and sets and things like that? Or do people feel like they have a pretty good handle on these things? I see Anirudh nodding yes, but I'm not actually sure what he's nodding yes to. Do you want to go over it, or?
We do sets. I don't really
Yeah.
get those.
Okay, let's do everything. Sure, great, sounds good. Okay. And thank you for speaking up. Anyone else have anything that they have like requests for? We can go over everything right now. Anyone? Okay, let's start with sets. Okay, so the way you create a set is pretty simple. You just okay. Let's call this S. If I were to use this empty braces notation, that would create a dictionary by default. So I have to create a set parentheses, something like this. And it'll get printed out as a pair of curly braces kind of, but so slow. Okay. So but when there's elements in the set, I mean, I get printed out as a pair of curly braces, but of course the difference between a set and a dictionary is that a set is like a set is like a list or things like that, you know, or tuple or whatever, except it's not ordered, right? It's not like that. It maintains the order that you added elements to it in. And also it's it has just a single copy of everything, a unique copy. So if I were to do S add 1, and I look at S, it has this curly braces and 1, right? If I do S dot add 1 again, and then I print out S, nothing changed because there's already a 1 in it. Does that make sense? Okay. So when would you use a set? If I have like a list of objects, 5, 4, yeah. Right. If I want to figure out like, okay, what are the unique elements in this list, I can just convert it to a set and let that do the work for me. It's a bit lazy, but that is also what Python allows you to do. So why not, you know, take advantage of that convenience? Okay. If you want to pop a specific element from the set, we can say s.pop 6. Oop. Wait, sorry, s.remove 6. Sorry, s.remove 6. And I'll take that out. If I do s.pop, that will pop an element from the list, but I don't necessarily know which one. So it's kind of random from my perspective. So you usually would use s.pop when you kind of want to clear a list while also like doing something as an operation on each element of the list, right? So maybe as I clear the list, I also want to print out each element. So that's where s.pop would be used. But the way that Python works is actually, as of Python, I think 3.6 or something like that, it guarantees that the keys, or sorry, it guarantees that the elements of the set will be arranged in numerically ascending order if they're numbers. That also works technically in previous versions of Python, but it's not technically guaranteed. Now it's guaranteed. Okay. If I want to completely just clear my set, I can do s.clear. You know, and you can do things like copy and stuff like that. Now, what gets interesting is when we have two sets, something like, let's say 1, 2, 3, or sorry, 1, 2, 4, and then, okay, if I want to combine these sets together, right? If I want to take the union of them, do people understand what it means to take the union of two sets? I guess this is a little bit of math and set theory, but Basically it's like combining two sets, right? The way you can do that is with this single pipe symbol, this single unary OR operator, right? And it just combines the two lists. That's a cool shorthand. And if you want to update S in place, you could do something like this. Or equals T, right? So the same way we have the plus equal symbol, we have this S symbol. So this adds the 3 to the S. Okay, now let me actually go back to using these values, S and T. Let's say I wanted to find the symmetric difference, right? Like what's...
What about intersections?
Yeah, so we should go to intersection. Okay, let's do intersection next. But S and T, this is the intersections. This shows you the overlap. So where it's both true for both of them. And if you guys remember what the OR symbol is and the AND symbol, right? When you're doing ORing and ANDing, this is how you represent OR in other languages, even though like Python allows you to do OR. In other languages, it would be using double pipes. And for AND, you would have 2 ampersands. If you think about what OR and AND mean, right? It's basically saying like, hey, do we have an element in this one or this list, right? And it's kind of just combining it if it's in either one. In this case, this AND, right? It's just combining it if it's in both. It has to be in S and in T. So it kind of makes sense that these shorthands, work. This pipe symbol and AND. Technically, there is like an official function you can use. Like you can use S dot union of T, right? And this does the same thing as the pipe symbol. Or you can say S dot update T. And this is basically the same thing as pipe equals. And out S. Yeah. And it updates it in place. Okay. And similarly, I can do S dot intersection of T. And that's basically the AND symbol. Or I can do S dot intersection of update T. And that's the AND percent equals symbol. I'll just show you how this works. Yeah. Make sense? Okay. Now there's some more interesting things you can do. Sometimes you want to find the difference between two sets. So like what's in S, but what's not in T or something like that. Or what's in T, but not in S. So that's what this symbol does. This symbol means XOR in like if you're using it for like Booleans or something like that. What does XOR mean? It means exclusive OR. So it means only one is true or the other is true. And it kind of makes sense when you apply it to sets in this way because you're saying it's only in one set or the other set, but not in both. And there's a bunch of other set functions, but these are the ones I commonly use. There's also S minus T. This gives you the difference of the two sets, but specifically it's saying what's in S that's not in T. So it's not a symmetric difference. It's saying specifically, I want to see what's in S that's not in T. Yeah, and I can actually, let me just show you the functions from W3 School if you want to see all of them. So add will add an element to the set, clear removes everything, copy copies. We went over difference and difference update. Discard is similar to remove. Intersection update. So is disjoint will tell you like if two sets have an intersection or not. And these are cool. Is subset and is superset. So you can just say is one set contained within the other one. But these are overall the important things for sets. So how do sets actually work? How does Python know like how long does it take for Python to know like, okay, has this element already been included in the list before? Let's think about that. So if you were designing a list, you have, let's say, a couple of elements in there, like 1, 2, or sorry, you're designing a set. You have these elements. Okay. Now I have S dot add 1. I'm running that. Let's say. What would I how would I check to see if one was already in this list?
Like just like how to code it?
Yeah, sorry. How would I check if like one is already in the set? Let's say the set library did not exist in Python. Let's say you were creating it from scratch.
Okay. I would just say if one in S.
If one in S, well, sure, you could do that. But let's get even more basic. Let's say this in operator doesn't work in Python.
Okay. Can I iterate through a set?
Yeah. Let's
Okay,
say
then.
Mhm.
Well,
So-
if in doesn't exist, I can't use range. Can't. Okay. That in exists. Okay. For element in S, if element equal 1.
Great.
Yeah.
Otherwise, if you, yeah, and then not found,
Mm.
then we,
Yeah.
right, we add it to whatever data structure contains S, right? Like, so this is our implementation of the add function essentially. Okay. What's the, I mean, I don't want to say problem. What, like, how long would this take in the worst case scenario?
If it's the very last element in the set, then it would take that, like the length of how many there are.
Or if it's not in the set at all, right?
Yeah.
That can take a long time if we have tons of elements. Now, since a set has to guarantee uniqueness, that's its like whole defining property. You need to like make that be as quick as possible. So what's a good way to do it? This is tricky. So let's do this. Let's say we have let's say we only are going to add the numbers 1 through 100 to our set. Okay. One thing we could do is basically or allocate. Let's make this 0 through 99. Let's allocate 100 spots, right? There's maybe like a list of size 100. That contains the set S, right? That contains the elements of the set S. And so if we want to be able to check if an element exists in S, what could we do? That's an interesting idea anyway. We haven't even really arrived at search algorithms yet. We'll get to that tomorrow. But there's a faster way to do it than actually what search algorithms would allow for. Okay, so let's say we have a list, and anytime we add an element to our set S, basically we just change this -1 to whatever number is there. Okay. So how do I check if 2 is in my set?
You would check in index 2.
Yeah. Right. How would I check if 88 is in my list?
Check in index 88.
Yeah. How long does that take? Not very long, right? I mean, it doesn't matter how many elements I have in my set. If I have 0, if I have 100, right? I know exactly which memory location to go to. I know exactly which point in my array to go to, and I only have to check that place, and I'm good. So that's actually how sets work. Now, they're not assuming that you only will add the number 0 through 99 to the set. But what they'll do is they'll use something called a hash function. Have people heard of a hash function? Is anyone familiar with it? Yes. Okay. Jacob's familiar with it. Nice. Okay. So hash functions are used a lot in computer science. So like, for example, let's say I don't want to store my password in plain text, right? Let's say my password is and no one, guys, no one take a screenshot of this, please, because this is my password. But let's say this is my password. Okay. Again, no screenshots. So sorry, password 1 exclamation mark. Thank you. So if this was my password and Google wants to confirm that I am who I say I am, they could just store this password on their servers, right? And so if I type in now my password into my Gmail account, Google just checks, hey, is this password match what we have in our servers? What's the problem with storing this text on their servers?
People can be hacked.
Yes, Tom Cruise is going to break in there, right? You guys have all seen that scene in Mission Impossible where he's just coming down from the ceiling, right? He'll just take the hard drive. So what Google will do is they'll actually hash it. So there's a hash function. There's a function called, or there's a class of functions called hash functions, right? And what a good hash function will do is basically it'll take some element and let's actually run this. And it'll return some value for it, right? It just maps to some number, right? And now it's really difficult to reverse engineer. So if I know the hash of something, I cannot come up with a value that will result in getting this hash, right? So if I knew this was my hash, I could not get my password from that. But Google can store my password's hash, right? And so they know that, okay, the only way basically that I could get the password hash to match is if I typed in the correct password. Does that make sense? So two properties of password, or two properties of hashing, right? One, it should be kind of hard to reverse engineer. And then two, like, it's not like, you know, it's easy to predict in terms of like, if I have two consecutive things, right, they will map to consecutive values, right? So if I do hash, if I like try to do the hash of 1, right? That's going to be, oh, no, sorry. Hash of A, let me do, sorry. Hash of A is this, hash of B is completely different, right? So it's not consecutive like that or well ordered like that. Now, what Python has now done for numbers is that the hash of a number is always going to be itself. So the way it works for sets, or the reason why this will like always print out in numerical order, is because the hash of a number is always itself. So all the hashes, all the numbers will be ordered by their hash, and all the hashes are in numerical order. But for strings, it's still like, you know, basically random. And what that means is that when I add elements to my set, what's going to happen is all I have to do is hash the element, right? And then I have to check in the slot corresponding to that hash value. Does that make sense? Now, the thing is, like, you guys saw that I got a, you know, negative value when I typed in my password, right? So what's going to happen is, I mean, I don't know if I'll get a negative value again because this is a different password. Is this it? No, I forget what my password was. Okay, there we go. So this is a negative value. So what is actually going to happen is it'll probably be something like modulo 10, right? It'll probably do something like this. Right. And so let's say the set starts off with like 10 slots. How do I know where to put, like, you know, this element in there? Well, I'm going to hash it, and then I'm going to do %10, and that's going to give me an index number, and then I'll put it in slot 5. Now, sets don't have indices to us that are exposed to us, but the computer needs to know where they are. So there are kind of indices under the hood. Does it make sense how it works? And does it make sense why you never need to actually check every single element? You just check the hash. And because the hash should be relatively unique for different elements, there should only be like 1 or 2 elements located at that index. So you just check that index and nowhere else. Does this make sense? Jacob? Yeah. Okay. So dictionaries work the same way, by the way. So that's why sometimes if you might try to add like a list as a key to a dictionary, and it'll say, hey, this is not hashable. Because what happens is for a list, it's mutable, right? You can always change the elements in there, which means you can change, you know, what the contents of that list, which means you can, the hash technically would change. And so like, it just refuses to hash list. So you cannot hash list. You can only hash tuples, right? Because tuples are immutable, right? They're fixed. And so you can use those as keys for dictionaries. But this is also why dictionaries and sets, it's very quick to look up items because you only have to hash it and then you have to check what's located at that index under the hood. Okay, so this is good intro to sets, and then let me just go to dictionaries very quickly. So dictionary is something like this, and then I can store values at a particular key, something like D5 equals 6. I can't use a list as the key. If I try doing this, it's going to fail. It's going to say, hey, non-hashable type. Right? If I try iterating through all the keys, if, let's say, let me add a few items to this dictionary. Right. I can iterate to this and say for K in D, print K. And so what'll happen here is it'll print out all the keys. If I want the keys directly, you know, I can also just say something like this, D.keys. This is of some type like dictionary key. So if I want to convert it to a list, I can just cast it as a list like this. I can also just extract the values if I want. Get this. So that's dictionaries in a nutshell. Basically, if an element doesn't exist in a dictionary already, you need to add it. But if an element does exist in a dictionary and I want to append the value, I can do something like this. Or sorry, I want to add 1 to the value, increment the value, not append. And then this becomes 3, right? Okay. Are people cool with dictionaries? Okay, nice. Okay, so we don't have time to go through too much else. There's just one, I guess, final, sorting algorithm I wanted to go through. And I think I'll have new homework assignment for you instead with dictionaries and lists. So, but this is a quick sort. I think it's pretty simple. So let's say we have a couple of elements, something like this. Okay, there's 7 elements in this list, okay, and it's not sorted. So what we want to do is we want to pick a pivot point. A pivot point is basically some place in the middle of the array. And what we want to do is we want to sort each side of the array. So everything that's greater than the pivot point should go on one side of the array. Everything that's smaller than the pivot point should go on the other side of the array. Does that make sense? Okay, cool. And then we use recursion to kind of sort things again. So what's our base case for quick sort? It is as usual, you know, when you have like a array of size 1 or 0, and then you can just return that in place because it's already sorted. Now I can pick a random pivot point. Oftentimes like a good pivot point might be somewhere halfway in the middle, maybe like really optimized algorithms find a way to find even better pivot points. And that somehow like it's good to use something that's 70% of the way in. But let's just use something that's halfway in. So something like this. And how do we pick the elements that should go to the left? Well, I don't know if people are familiar with for loop comprehensions or list comprehensions. But this is a one-line kind of way to create a list and using a for loop, but inside of one line. So what this is saying is for every x in array, if x is less than the pivot, let's keep that x. Otherwise, don't do anything with it. And so we don't take that value. So this gives us all the values for on the left. This will give us all the values on the right. And this will give us all the values in the middle. Okay. So now we have 3 lists, left, mid, right. We've not fully sorted them, but like we're sorted them in the sense that we know that, okay, everything to the left of this pivot point is smaller. Everything to the right of this pivot point is larger, and everything in mid is the same as the pivot point. Okay. So in order to return a sorted version of this array, we should just sort the version on the left. The middle is already sorted because it's all the same, or it's maybe just an array of 1 number. And then we want to sort the version on the right. Sorry, this should be, I guess let's make this middle. Yeah. Does this make sense? And so that's quick sort. And we can just basically pass in X and check this, and it sorts correctly. Does that make sense how that works? Okay. Do people have any final questions?
So the sort that actually exists in Python right now, what kind of like algorithm does it use?
Good question. It's something called TimSort. Anyone want to guess what the name was of the guy who made TimSort?
Adam?
It's close. It's actually Tim Peters.
Oh,
So
really?
yeah, I know. It's crazy. So it's kind of similar to like merge sort. Also has some similarities to quicksort, but we'll talk about it tomorrow. Essentially, it actually is relatively as quick to run as quicksort and merge sort. The problem with merge sort is that like in order to do it easily, you usually have to allocate like a new array, and it takes time to create a new array. Quicksort you can do in place. So quicksort is usually preferred. TimSort is though good as well, but TimSort is better for things where like you have complex data structures, like list or sets or stuff that you want to sort as well. Yeah, quicksort it's a little harder to do those things. Okay, so but yeah, I think we're at time. If there are no final questions, we'll end class. Everyone good? Okay, cool. I'll see you all tomorrow. I'll try to push out a homework assignment in the next half hour. Okay, see you guys.
Thank you.